So the second topic of after Latimer diagram is the frost diagram. So first, what is a frost diagram? It is a plot of a product of oxidation state and reduction potential against oxidation element. So in the Latimer diagram, we only focus on the oxidation state and reduction potential. In this, you have to multiply oxidation state and reduction potential and plot it against oxidation state of an element. So in this you have to, there are some observations of Latimer diagram. The first observation is that the species which is lower, present in the lower on the diagram, is highly thermodynamically stable. It means if we have plotting a plot oxidation state as well as reduction potential against oxidation number, and this is, let us suppose, B point. So this is highly thermodynamically stable one, that is, it is the lowest point. Second observation is species located on the upper right side of the diagram will be a strong oxidizing agent. It means the element or species which is located on the upper right side means this D, it is highly a strong oxidizing agent. And the third observation is which is present on the left side is a highly reducing agent. So I have taken an example. Let us suppose any of the species is given, Latimer diagram of any of the species given in the paper. I have taken thallium. This is a Latimer diagram of thallium, that thallium 3 positive converting into thallium positive, and then thallium reduction potential values are given on the above. You have to convert this Latimer diagram into a frost diagram. So first we have to find out the Ne naught value, means you have to find out the multiplication of oxidation state and its reduction potential, then you can plot it. So first I have taken first the thing which you have to remember is you have to draw this diagram with respect to the lowest oxidation state. So in this lowest oxidation state is 0. So I am taking with respect to thallium 0. So thallium is converting into thallium positive. So electrode potential value is given 0.034 volt, and the N value, what is the change in oxidation state, that it is +1. So N value is 1. So any value I have calculated here is minus 0.34. Similarly, thallium to thallium 3 positive. So electrode potential value is 0.3773. So change in oxidation state is +3. So I have multiplied this. This comes out to be 2.19 volt. So you have to plot a diagram. So I have plotted here, that is Ne is along the oxidation number is along the x-axis, and product of oxidation state and electrode potential on the y-axis. So starting from 0, 1, 2, 3, 4 here, and in this -1, I am starting from -1 because one of the value is in minus, that is 0.34 volt. That's why I have started from -1, 0, +1, +2, +3. So in the first case, if I am taking about thallium, that is thallium 0. So the oxidation state is 0 here. So if you multiply any reduction potential with 0, it comes out to be 0. So first I have drawn a thallium 0. Then the second one is a thallium positive. Then thallium positive is minus 0.34 volt. So it comes between 0 and -1. So against +1 I have drawn here. The next one is +3. So the lowest point is this one, thallium positive. So this is thermodynamically stable one. Thallium positive is highly oxidizing agent, and thallium 0 is highly reducing. This is how you have to draw the reduction frost diagram from a Latimer diagram. This is very important. It comes in the final examination of Punjab.